All right, guys, the plan today is to look at how could we take our similarity conditions, so side, 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 and angle similarity, and turn them into congruence conditions. And I'm going to shrink down now. By the way, this size now is now similar to how I was before, connecting a little bit of math in there, did a transformation. All right, guys, so up here on the left, we've got these similarity conditions, side, 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 and angle. We're going to quickly review what each of those is and then see if we can turn it into a congruence condition, a way to test if things are congruent or not. So let's remind ourselves what these things mean. So let's start out with side, side, side. So if we're looking at side, 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 apparently I was on my eraser, not my pen, oops. All right, side, side, side. Let's remind ourselves what that is real quick. So to prove that two shapes are similar using this, and these have to be triangles, you would have to have two triangles. You'd have to know all three of their side lengths. For example, maybe this is 2, maybe this is 3, maybe this is 4. And then we'd have another triangle. And basically what this is saying is that the ratio from each side to its corresponding side has to be the same ratio, meaning they all have to be multiplied by the same amount. So for example, they could all be multiplied by 2. So maybe this would be 4, and this would be 6, and this would be 8. These two triangles would be similar by the side, side, side similarity condition because they are all sides have been multiplied by the same amount, and we've proved this before. What we're looking at now is, could we adapt this to congruence? Well, what is the difference between congruence and similarity? Similarity, informally, basically means two shapes are the same shape but could be a different size, meaning they could be dilated. It means that you can map one shape directly onto the other one by using just rotations, reflections, and translations, but no dilation. And then in similarity, you can use a dilation. In congruence, there can't be a dilation. It has to just be rotation, reflection, and translation. The shape can't stretch at all. They can't be different sizes, which means if you looked at the ratio, which in this problem was 2, that can't be 2. If there was a ratio, that ratio would have to be 1 to 1. So for these to be congruent, this can't be those measurements. It would have to be, the 2 would have to stay 2, the 3 would have to stay 3, the 4 would have to stay 4. They have to be the same shape and the same size. They could just be rotated or flipped or slid around. That's a translation. So if this was the case, and then our ratios here were all 1s, would these two shapes be congruent? Yes, because we've already proved that these two shapes would be similar, and then if their ratio is also 1, if that's what we limit this to, then they would also be congruent. So there is also a side, side, side congruence condition, and the difference between the similarity version and the congruence version is that in similarity, you're checking the ratios are all the same. In congruence, you're checking that the side lengths are all exactly equal, not just the ratios. I should turn off my notifications over there. So that's the difference. If you do check the ratios have to be 1. All right, so we've managed to get that to turn into a congruence condition. Let's see if we can do the same thing for side, angle, side. All right, well, let's remind ourselves, what was our side, angle, side similarity condition? That was when you had two triangles, and in those two triangles, you knew 2 of the side lengths. So for example, maybe this was 2 and this was 3. And then you also had to have the angle between them. So maybe this was 30 degrees. Okay, well, in your other triangle, you would have to also have a 30-degree angle. That's the A, that's the matching angle part. And then the side lengths that surround that angle, that's why the A is between the two S's. It is the angle located between those two sides, or in other words, those are the two sides that create that angle. Those two sides don't have to be the same lengths as the other ones, but they have to be multiplied by the same amount. The ratio has to be the same. So for example, this could be 4 and this could be 6. 3 isn't the same thing as 6 and 2 isn't the same thing as 4, but they've both been multiplied by the same amount. Those 2's are equal. That's what matters here. Now, could we do the same thing for congruence? Well, these two things would not be congruent if they didn't have the same lengths. these lengths would have to be the same. Like this would have to be a 3 and this would have to be a 2. These things could not be multiplied by 2. If they were multiplied by anything, it would have to be 1. But if we had this, would they be congruent? Yes, because to be congruent, you just have to be similar, but also be the same size. So if side angle side proves that they're similar, and that ratio ends up being 1 between the two shapes, meaning the sides are actually exactly the same length, it would also prove that they are congruent. So that means we can adapt our side angle side similarity condition into a side angle side congruence condition. And again, what's the difference? In the similarity version, you're checking that everything's been multiplied by the same amount. In the congruence version, if they're multiplied by something, it's 1, meaning the lengths are exactly the same. So you're checking all the lengths are exactly equal, not just that the ratios between the lengths are exactly equal. All right, let's move along here and take a look at angle-angle. So remember the angle-angle similarity condition. This one is basically saying that the 3 angles in the triangles match. It's only listed with 2 angles written down because if 2 angles in a triangle match, the third one automatically matches because the angles in a triangle always add up to 180. So if 2 of your 3 numbers are the same, that third one has to be the same because there's only going to be one possible number to add to those other 2 to equal 180. So basically we're saying that if this angle matches this angle and this angle matches this angle, these 2 triangles have to be similar because all of their angles match, and we've again already earlier this year proved that that works to prove similarity here. But now we need to think, would this also prove congruence? Well, to be congruent, they don't have to just be similar, they also need to be the same size. Do we have any reason to believe, just based on the angles, that these would be the same size? I would argue no. In fact, I could take one of these, and I believe I can stretch it, can't I? I think this program can do some stretching. See, look, it's bigger now, but the angle itself hasn't changed. Its size has changed. It's been dilated, but the angles stay the same under a dilation. So two shapes that have matching angles, 2 triangles that have matching angles, are similar, but they're not necessarily congruent. So here's the thing. To adapt this to be a congruence test, you're going to have more information than just knowing the angles match. You are also going to have to know that the sides match. Now, angle-angle does prove they're similar. So to prove all the sides match, you really only need to know that one of the sides matches. For example, this one might match this one. That would be enough to prove that the triangles are congruent. Why would it be enough? Well, because that's in a corresponding position. This angle up here is located between, on the top triangle, is located between the same 2 angles as the one on the bottom triangle. So it's in a corresponding position. And we know that if these are equal, we know that the ratio between these is 1. And all of the ratios then would be times 1 because the triangles are similar. And similar triangles would have the same ratio between all of their sides, which means that if you know that the angle, that the side located between those 2 angles matches in both of these triangles, then we would have a congruence condition. In other words, you would have the angle side angle congruence condition. The S being located between the 2 A's to indicate that we're saying that the side pair that matches, the sides that are the same length, is located between the 2 angle pairs that match. Okay, but is that the only place the matching sides could have been located? No. Let's think about this a little bit more. Whoops, I wanted to just erase the blue bit. Okay. Let's think about this a little bit more. Here's what I'm getting at. If I knew that this one matched this one, it would not be a congruence test because just because these are the same length, maybe like this is 2 and this is 2, but if this is 3, then our corresponding sides are not the same length, and these 2 triangles are not congruent. They're not going to all have matching sides that are the same length. So that doesn't work. It's not just that you have 2 sides that are the same length, they have to be in the same position. But it doesn't have to be the position between the 2 angles. It could be one of the sides that's not between the 2 angles. If we knew that these 2 sides matched, what matters is that they're in a corresponding position. That's what matters. So it could either be a side that's between the two angles or a side that's not between the two angles, as long as that's true in both of the triangles. So this would also work because if these are equal, their ratio would be 1. All your other ratios would be times 1, and all your sides would end up being the same length. Again, because you have to have a corresponding pair that matches. This one usually gets written down as what's called the oops, didn't mean to open up my menu there. Go away. All right. What was I getting at here? So this one is usually written down as, well, not the angle side angle. It's a little bit different because of the location of the side. You have both angles, and then you have a side that's not between the two angles. And that gets you the angle side congruence test. Now, this is pretty much all of them, but there is one special case that we will see come up sometimes, which is sometimes we have a right triangle. So sometimes we specifically have a right triangle. And if that's the case, you get something called the hypotenuse leg congruence test. Oh, what is that? Well, let's take a look here. So let's draw a right triangle. So right triangle, let's mark our 90. Let's mark our 90. Okay, so there's one called the hypotenuse leg test. Let's just look at that one directly, okay? In the hypotenuse legs test, they're saying that your hypotenuse is the same length in both of them. Remember, your hypotenuse is the side across from the 90. Not the two sides that make the 90 are called the legs, and then there's the one across from the 90 that's called the hypotenuse. The hypotenuse matches, and let's say that you have a pair of legs that match, like these two, for example. Okay? I meant to make that a different color, but whatever. These would have to be congruent. Why would these have to be congruent? Well, there's a couple of different ways that you could look at it. One way to justify this, though, is in a right triangle, we know the Pythagorean theorem has to be true, right? A squared plus b squared equals c squared, right? That has to be true in any right triangle. And if you know that these two match, that could be like your A and your B. Does that make sense? Like these two match. So if you solved for, sorry, that would be like C because it's a hypotenuse, isn't it? Okay, sorry, that could be like your A and your C. So if you have your A and your C, and then you use the Pythagorean theorem to solve for this other side, then this other side, B, would have to come out the same because you'd be solving the same equation. Like I'm saying those would be the same because you're solving the same equation using the same two numbers to get that answer in both triangles. So it has to be the same if we know the Pythagorean theorem is true, which we've already proved. Which means that if you just know that the hypotenuse and the leg matches in a pair of right triangles, it means that the two triangles will be congruent. That is called the hypotenuse leg congruence condition. And this is all of the congruence conditions. So let's do a quick practice problem. So what are you actually going to be asked to do with these? Usually you'd be given two triangles, and you know some stuff about those two triangles. And the question is, are the triangles congruent? And if they are, which congruence condition do they meet? So let's take a look at that. So what if we were told that we had a 20-degree angle in this triangle, a 20-degree angle in this triangle? We knew that this was a 3, this was a 2, this was a 2, this was a 3. Question, are these triangles congruent? And if so, which congruence condition do they pass? Well, so let's just take a look. What kind of information do we have? What is the structure here? Do we have 3 side lengths? No, so we're not going to do the side test. Do we have 2 sides with the angle in between them? Do we have 2 sides with the angle in between them? Yeah. And do those 2 sides match? Meaning we have the 3 matches the 3, we have the 2 matches the 2, and the angle between them matches. That's going to be your side angle side test. So that's the idea of how to use these. You just look at the type of information that you're given and figure out which of those congruence conditions that it passes. Hopefully this video was helpful to you. And have an excellent day.